Hello, this is video presentation of Group 1 for audio filterings. My name is Tan Yawi and I'm going to explain for the input as well as the time domain plots. So for the inputs, we are going to use audio reads as well as audio info to obtain relevant info and import our audio file into MATLAB workspace. So the function is going to work like this, visual in MATLAB, and the audio info is going to display a lot of valuable information such as sample rate as well as the duration of the files. Next thing is we are going to plot continuous time signal using this function over here. So I have already defined the times domain using these functions, and we can just simply plot all our continuous time signals, and as well as we can also provide some labelings into the signals. I have also included a subplot to include more files in a single windows. So as you can see in this figure over here, you can see the x label amplitude as well as time, as well as the x-axis from 0 to 2.5 seconds. And that's all from me for time continuous time domain and as well as the input. I will pass to the next person. Thank you.
Assalamu alaikum, my name is ADIB Mohammed and I'll be presenting how we can represent the input signal to frequency domain and why we do it. But first, a brief description of what our project is. So we have a signal which is presented in time domain, and then we convert it into frequency domain from which we can identify the noise frequencies, and we design filters to remove these noise frequencies and have a clean audio. So to convert to frequency domain, we use the function FFT, input signal, and number of samples. However, this causes discrete Fourier transform having discrete frequency k and not discrete time Fourier transform. But we can easily convert to have the frequencies in omega or in hertz using this and this formula. So I wanted to display in hertz. To plot the magnitude spectrum, we use ABS function, and for phase spectrum, we use the angle function. So from the graph, we can see a high amplitude pitch at 800 hertz, and some noises are after 2400 hertz. So from this, we can identify our noise frequencies are 800 hertz and frequencies after 2400 hertz. Thank you.
Hi, I'm Yo. Now I'm going to present about the filter design to remove the white noise. From the Fourier transform figure here, I learned that the location of the white noise is about 2000 Hz. In order to remove the white noise, I use IIR Butterworth low-pass filter to remove it. The order I use for the filter is 5. Of course, the higher the order, the perfect the filter will be. The cutoff frequency is about 2000 Hz, which is the location of the white noise. The voice range I use here is 1.5 kHz. And this is the time domain of the unfiltered and filtered audio signal. And this is the magnitude spectrum of the unfiltered and filtered audio signal. The output audio will be free from the white noise, but the short noise will still exist.
Hello, I'm Yap, and my part is to explain the IIR notch filter to eliminate the shoot noise. Here, as you can see here, the shoot noise is 800 Hz. So we are going to use the IIR notch filter at 800 Hz, and the bandwidth is 0.01. And as of course we know that the smaller the bandwidth, the better the filter is. And here we can see that we are able to filter out the shoot noise at the 800 Hz, and this is the filter out, the output of filter in frequency domain. The shoot noise is filtered up, but without the low pass filter, the IIR butter filter, we still has the white noise over here. Okay, thank you. That's all from me.
Hi, I am HERN, and I will continue with the Z domain analysis for these two IR filters that we designed. To do the Z domain analysis, or we say Z transform, it converts the discrete time signal, which is sequence of real or complex number, into complex frequency domain. By using the Z-plane function in MATLAB, it can direct plot the zero and pull in a figure window. What we use the input is the coefficient B and coefficient A. To get this, we use the convolution. After we run the code, we will get the pull and zero plot. From this, we can see our system has 7 pole and 7 zero, and the system is stable since the unit circle is inside the RC.
Hello, I am Rifky Pramudita Mahendra. Before this, we have talked about designing noise filter using IIR method. But do you know that there is another method of filtering? Yes, it's by using FIR filter. How is it different from IIR filter? As you can see here, we have designed both IIR filter and FIR filter. On the left, we have filter for human voice range, which is around 400 Hz, and on the right, we have filter for short noise, which is at 800 Hz. And these are the output for both filters, red for the FIR and blue for the IIR. From here, we observe that FIR filter has less effect on the magnitude of the passband. Thank you.